bracket, but it's not written down explicitly. But like then we heard like from Luca about like this path integral idea, and like we also worked this out, and later recently like we realized actually like back in the 2000s, there are also people like in the quantum Hall community, they have essentially the same story, but just in the quantum Hall context.
I see. I
Yeah,
see.
yeah.
Yeah, that's great. That's great. I look forward to hearing about it. So, although
Mm.
you only see like about 10 people on Zoom, but actually this talk is also broadcast via
Mm.
Codes, and usually about 3,000 people watch it.
Oh, okay, great. Wow,
So now you are being watched by 3,000 people.
that makes me a bit nervous. Yeah.
Can we start now?
Yeah, yeah, sounds good.
Okay, let me start recording.
Recording in progress.
Okay, it's a great pleasure to have Professor Mengxin Ye from University of Utah to speak here today. Mengxin got her PhD degree in physics from University of Minnesota under the supervision of Professor Andrei Chukov, and then she worked as a postdoc at KITP, and now a professor at Utah. Over the years, Mengxin has worked on many types of quantum materials, ranging from Kagome metals, twisted valley graphene, K-type materials, some other quantum spin liquids, and high temperature superconductors. And today she's telling us about the more formal aspect of her work. Let's welcome.
Yeah, great. Yeah, thanks, Liu Jin, for having me. Hi, everyone. It's my great pleasure to share with you about our recent progress and efforts to understand how to bosonize a Fermi surface when there is a magnetic field. And these were a series of works done in collaboration with Yuxuan Wang, who is a faculty at University of Florida. So to begin, I want to use this opportunity to make a small advertisement for our PhD program. So I'm at University of Utah, and now I'm looking for motivated graduate students who are interested in quantum materials and the strongly correlated electron systems, and study the series of them. And if you are interested in these directions and also want to enjoy the beautiful neighborhood of Salt Lake City, please feel you are very encouraged to consider applying for our PhD program, and you can find more information on my website. And by the way, this background is a picture I took last year when I visited the mountains, just a 30 minutes drive from the city. Okay, yeah, let's get back to the physics. So to begin, let me first give you a very basic overview of the orbital magnetic responses. And I hope to convey to you that, well, it sounds a very conventional, a very old subject. There are actually still things we can try to understand better. And there are also more profound things for us to understand. So let's consider a very simple setup. Consider a magnetic 2D electron gas or 2D electrons and apply a magnetic field perpendicular to it. And we know from classical mechanics that the electrons will undergo these cyclotron orbits. And here I draw the cyclotron orbits, and inside the bulk, so they can finish a closed orbit. And while the electrons on the boundary will go along the surface, the boundary. And if you add up the contribution of magnetization from both the bulk and the edge, you will find that classically the magnetization has to vanish because of the cancellation between the edge and the bulk. So any magnetization, like from this orbital motion of electrons, has to come from the quantum mechanical effects. And we can quantify them by computing the thermodynamic potential in the presence of a magnetic field. And let's consider the semi-classical regime. So where this cyclotron energy is much smaller than the chemical potential. So that means below the chemical potential, we can fill in many Landau levels. And then, let's ask what is the response or what is a magnetization we can extract from the thermodynamic potential. So if we take the derivative of the thermodynamic potential, the oscillatory part of the thermodynamic potential, we will get this oscillatory magnetization. And it appears when the temperature is much smaller than the energy spacing of the Landau levels, the cyclotron energy omega c. And as you can see here, I plot the energy as a function of magnetic field, and we can see this oscillatory behavior. And if we increase the temperature, so this oscillation amplitude can be smeared due to the thermal fluctuations. And as we further increase the temperature, we will get this very smooth curve. And that is for 2D electron gas, that is quadratic in the B field. And this gives us the magnetic susceptibility, which is like second order derivative in B. And also for some bands with barrier curvature that spontaneously breaks time reversal symmetry, we can also get the magnetization at linear order in B. So these are all response theory. And the point is that once we obtain this thermodynamic potential, we can get the quantities we want. And very interestingly, when there is a magnetic field, we can get oscillatory behavior. And here I want to understand the oscillatory behavior, which is a quantity that is most mysterious to me. So let me use this very simple LK formula for 2D electron gas to explain why it is an interesting quantity. So this oscillatory part of the thermodynamic potential can be written into two parts. So this part is the cosine part. We can say that this phase depends on the ratio of the Fermi surface area and the magnetic field. So, and that gives us an oscillation in 1 over B, and the period is determined by the Fermi surface area. And interestingly, this oscillation period is a universal quantity. And it has been shown with examples that it cannot be changed by interactions as long as the Fermi surface is intact. And
sorry. You said it has been shown by examples, or has it been shown rigorously?
So by rigorously, my understanding is so from say Dominic's work, they use an anomaly to show it. Is that the example you want to see?
Oh, okay, yeah.
Is that the theory? Yeah. There has been some work in terms of anomaly that makes a statement that it's a universal quantity. Yeah.
I see. You mean the period is universal?
Yeah. The period is universal. Yeah.
So then what about the prefactor? Is the prefactor a consequence of a particular dispersion of 2D electron gas?
Yeah, I think it will depend on the particular dispersion, but it's actually a quantity that is depend strongly on the fluctuations near the Fermi surface. So near the Fermi surface, I think this Landau level approximation is not too bad. So maybe it works, but indeed, so it's not a very well known, very clear to us that for other dispersions, and also when there are barrier curvatures, what is this amplitude, the prefactor? Yeah, this is
As
also one question we hope to understand better using this
yeah.
EFT, this bosonization approach.
Yeah. So if the omega c is much smaller than mu, I guess we can still expect even the amplitude can be expressed in terms of quantities only near the Fermi surface. It doesn't matter, may not matter what is deeply below the Fermi surface.
Yeah. I think that's the case. Yeah. In particular, so let me show you this curve. So this curve shows how this amplitude as a function of temperature, what's the ratio of this amplitude as a function of temperature, and the amplitude at zero temperature. So this is one like at zero temperature, and it decreases as temperature increases. So at least this part, so this difference must come from thermal fluctuations, and that is only important from fermions near the Fermi surface.
I see. Thanks.
Yeah.
I think Via has a question.
No, sorry, I just wanted to comment. I think that doesn't the universality follow from what people call Luttinger's theorem, just the fact that the area doesn't change?
Yeah, the Luttinger theorem, my understanding is, yeah, it's connected, but it's not the same. So the Luttinger theorem states that if you add interactions, the area of the Fermi surface only depend on the is related to the UV quantity, the electron density. But here the statement is like for this oscillation amplitude. So what it whether it only depends on the Fermi surface area.
I see. Thank you.
Yeah. So it's a slight different. Yeah.
Thank you.
Yeah. I hope to convey to you like later using this our approach that also why it only depend on the Fermi surface area. Yeah. Okay. So here now we are about at the oscillation amplitude. So for this equation is obtained for like a 2D free electron gas. When we add interactions, if we consider a Fermi liquid, it turns out the correction to the LK formula is very trivial. We just need to replace the mass to the effective mass in this cyclotron energy. However, when we consider like strongly correlated Fermi surface, say the non-Fermi liquid or marginal Fermi liquid, recent work shows that the amplitude as a function of temperature will like have different scaling behavior, exactly due to the fluctuations near the Fermi surface.
So just to make sure, about this result related to Fermi liquid, did people derive the LK formula just within the Fermi liquid theory by focusing on the Fermi surface?
Yeah. So let me think. Right. So what people did is they calculate this thermodynamic potential, and it turns out it can be written in terms of the Green's function and the self energy, and they just calculate these quantities explicitly.
I see.
And for the self energy, but you know that if you capture a Fermi liquid in terms of Green's function and self energy, you already assume that it's near properties near the Fermi surface.
So this calculation is assuming that the effective mass is a constant around the Fermi surface, and there's
Right.
There's no vary phase.
No, they only consider the quadratic band.
Oh, they also assume Galilean invariance.
Yeah, right.
If there's no Galilean invariance, then what happens?
I don't know. I don't think current literature has discussions on it.
I see. Thanks.
Okay. Yeah. So, well, we have a lot of understanding of quantum oscillation for this like a simple like quadratic band. However, when this quantum oscillation has been used widely in experiments when we study quantum materials, for example, we can use this oscillation period to extract the area of the Fermi surface. And on the other hand, this like very old quantities still like give us a lot of puzzles. So besides the question that Liu Jun asked, that I totally agree, like how to generalize it to interacting topological bands. So there are also very like big puzzles in this community. For example, why we can see quantum oscillations in some insulators, such as Kondo insulator and excitonic insulators, and also in some iron-based superconductors, people have seen like new frequencies that depend on the difference of Fermi surface areas. So you can see that all these questions are related to how to understand this magnetic response when there are strong correlations. And so in this talk, I'm not going to like address any of these questions. So instead, I want to show you an effective field theory approach to study the Fermi surface in a magnetic field. And hopefully it can incorporate interactions and also the quantum geometrical properties of a Fermi surface like in an economic way. So that's like hope we have, and currently we also have some progress. We think it's working in a good direction. So first, let me like explain why we want an effective field theory, and also what kind of effective field theory we want to get. And to begin, let me like review the standard approach to get the magnetization oscillation that I showed earlier. So if we have like we start from a parabolic band, and we know how to solve the non-interacting problem, and it gives us this bunch of Landau levels. And we know that at each Landau level, we have a number of degenerate states determined by the ratio of the total flux to the system over the magnetic flux, the flux quanta. And also each the energy spacing of the Landau levels are omega c. And then what we do is we project the interactions or thermal fluctuations or include the thermal fluctuations like near the chemical potential. And then we can like study find the magnetization oscillation that only depend on parameters near the Fermi surface, like the quantum critical scaling from the non-Fermi liquid and effective mass for the Fermi liquid. Well, this approach works okay for interactions plus parabolic band. It turns out it's very challenging to proceed with this approach when we consider interacting topological bands in a magnetic field. And the reason is because we don't know how to solve the spectrum and wave function for a topological band in a weak magnetic field very efficiently. So in the literature, what people do is they either take a semiclassical approach, which is challenging to be generalized to the strongly correlated case, or they try to find more efficient approach to solve a topological band in a magnetic field. And if we want to get some analytical understanding, I think a new method is needed. And as we have seen from the examples, so these quantities related to quantum oscillation are determined by properties near the Fermi surface. So hopefully we can have a low energy effective field approach to like understand this problem. And so there are two possibilities we can think about for low energy effective field effective theory. So one approach is we can try to develop a low energy EFT just for the these Landau levels and the fluctuations between the Landau levels. And this idea have been developed in the literature, like by like several people. But the problem, I think, is that if we want to generalize it to topological bands, it's very challenging because our problem is that we don't know how to solve the non-interacting problem efficiently. So instead, we are going to take another approach. So we want to ask how to like write down the effective field theory first for a Fermi surface in zero magnetic field. And then we want to ask how to couple this like low energy EFT to a background gauge field, the background magnetic field. And then we like analyze this coupled theory. So this is the approach. This second approach is the one I'm going to take here. And so let me pause for a second if there is any questions. Okay, so let me start with introducing the effective theory for like a Fermi surface at zero magnetic field. So let's start with just simple free electron gas. So we know that we can describe this like electron like this parabolic band by its Fermi surface. And here I draw the Fermi surface with a Fermi like momentum PF. And we know that the ground state distribution function is 1 inside the Fermi surface and 0 outside the Fermi surface. And then like if we want to like, but this like distribution function is actually not complete. So it can be written in terms of phase space coordinate. So both x and p. So here x denote the space in the like denote the function in the position space. So for the ground state, we can say that at every position xi, so the distribution function follows this like theta function. And like when we ask how to describe the dynamics of the free electron gas, so we can ask how this distribution function evolves space-time when we add some like perturbations to it, or namely when the Hamiltonian is not just the this epsilon. So we can, for example, we can add a potential, and it turns out that the equation of motion of the distribution function follow this well-known semiclassical Boltzmann equation. And when we
question. So what's the definition of this distribution function?
Yeah, this is essentially defined as like it's defined as a density operator, like projected to the to the Fermi surface.
Yeah, but the density operator, basically, I'm asking how does x enter here?
Yeah. So yeah. Okay. So it's I will like explain it a bit in more detail later. So you can see that, yeah, let me just say like a few words here. So you can see that this C we normally like put density operator as C dagger C, and we subscript P for both. And however, like this is like a bilocal fields. So this denotes one position and this is another. So and these two can in principle be different. And so this x and p actually means the following. So for this C dagger, let me use this annotate. So it's C dagger x plus y over 2 and C x minus y over 2. So this is like the C dagger C, but at a different position. And then I do Fourier transform for the relative coordinate. and then I will get a function in terms of x and p. And
So
x is a center.
So the expectation value of this operator in the ground state is this f.
So here, for this one, it's in the ground state. It's this f, Right. So this x is a center of mass coordinate, and the p is a relative coordinate.
I see. Thanks.
So, sorry, just for clarification, this is consistent with the Wigner function like usually defined, isn't it?
Yeah, exactly. It's exactly the Wigner function. Yeah.
Okay, thank you.
Yeah. Okay. And this Boltzmann equation can also be generalized to interacting fermions. So here I'm not going to discuss the details, and just want to say that the philosophy or the idea is that when we add interactions, so we don't have a we don't have a particle, but we will have a quasi particle. And it has many properties, same as free electrons, meaning that it has a pole in its Green's functions. And for that case, we can also formulate the Boltzmann equation by taking into account these interactions. And the question we want to have to address is how to develop an effective field theory for the Fermi liquids. And so this effective field theory should be able to give us this Boltzmann equation I described. And in the literatures, there have been multiple and very long-term attempts to construct a bosonized EFT to describe the fluctuations of the Fermi surface, whose equation of motion is a Boltzmann equation. So in the earlier days, people have used generalization to the 1D bosonization by separating the fermion on this Fermi surface into patches. And for each patch, we can formulate a 1D bosonization, and then we can try to match the patch. So this approach sounds really very difficult for me. And then recently there have been a very interesting proposal led by Dan Song's group in Chicago. So I will use DDMS to be short for this work. They developed an exact nonlinear bosonized EFT. And in this talk, I'm going to follow this the derivation achieved by them.
Can I just ask one high-level
sure.
question? So why do you need to go all the way to bosonized EFT to get the Boltzmann equation? Doesn't it just follow from the operator equations of motion for that thing you wrote down, the C dagger C?
So you mean why?
Yeah. Why do you need to go all the way to field theory when you have this object C dagger C that has dynamics that you can derive?
Yeah. If I want to ask, so let me see if that's a question you ask. So if I want to ask how to get this Boltzmann equation, I don't really need to bother with developing an EFT.
Yeah.
So my goal is actually the opposite. Yeah, maybe I should make it clear. Yeah, my goal is to develop to know what is an EFT for the Fermi surface. By EFT, we mean that the fluctuation, in terms of fluctuations near the Fermi surface. And my logic is that this EFT should be able to reproduce the Boltzmann equation.
Okay, thanks.
Yeah, because at the beginning, I say that I hope to get a low energy EFT, and then we can couple it to the gauge field.
Okay.
Yeah. yeah, so right, so let me just make what I said like in words be a little bit more concrete. So we start with a collisionless semiclassical Boltzmann equation, and where this bracket is the classical boson bracket, and we know that to solve this like semi-classical equation of motion, we can this is a solution. And then it can be viewed as a Coadjoint-orbit of the F0, the ground state distribution, and the group of canonical transformations. So this is essentially what we learned in classical mechanics. And the question is how to write down the EFT, whose equation of all this Coadjoint-orbit, and namely, in other words, whose equation of motion is a collisionless Boltzmann equation. So this is what I want to describe next. And so here I'm going to take a different approach than the approach outlined in the original DDMS paper. But this approach, I should say that, well, it's to my knowledge, the first appeared in our work, but it follows the idea described by Luca and Uma. And also, there have been earlier developments in this direction in the quantum Hawk context. And so let me introduce this like how we obtain this EFT by making analogies with how we obtain the path integral for single particle quantum mechanics. We know that in quantum mechanics, if we want to obtain what is the transition amplitude from one state Qi to another state Qf under this time evolution, then we can partition this time slice from 0 to capital T, partition this time to small slices. And at each slice, we insert an identity written in terms of the like the summation of the Hilbert space of the Hilbert, all the states in the Hilbert space. So it's the same here. So here, one thing we want to compute what is the transition amplitude from the ground state Fermi surface, like back to the ground state Fermi surface following this time evolution. And for simplicity, let's just consider a quadratic Hamiltonian. And like at each time slice, we also want to insert states in the Hilbert space. And we need to ask what are the states we want to insert in the Hilbert space. So naively, or intuitively, we can think that these states are just deformations of the Fermi surface. And so they can be parameterized as this state U here, which is like written in this way. It's an exponential of like a fermion bilinear operator acting on the ground state Fermi surface. And this fermion bilinear contains two positions, I and G. And we also have a parameter called phi here, and it is also the function of I and G. And we basically can insert all the states in like written in this form into the into the time slices, and that gave us the following path integral. And next we want to.
So here, when you say 1 is equal to this quantity, you really mean the projector into a sector with a fixed particle number is equal to this quantity.
Right, yes. So because the logic, the argument is that the Hilbert space we are talking about is a Hilbert space that can be reached by the Hamiltonian, and this Hamiltonian preserves the particle number. So that's why we only need to consider this type of states.
So do you mean you can show that the integral of this U is indeed the projector?
the integral of this you I didn't show it explicitly. Yeah, so by show you mean that yeah,
I mean,
okay. So are you yeah,
can
please.
you prove this equation 1 is equal to this integral?
I didn't I think if I have a Hamiltonian that preserves the particle numbers and also it's a quadratic Hamiltonian, then yeah, then I cannot say I prove, but I can use a group theory argument to show that these states are the only states that sit in the like the right representation. So let
But
me see.
this is not saying that the integral is really 1, right?
Okay. So by saying that this is certainly not all the states in the Hilbert space.
Yeah, but
Maybe
if we
that's
only
why you are concerned.
if I only consider states with a fixed particle number, are you using something like the Schur lemma or
Well, if yeah,
Liu
let
Jun,
me
perhaps I can give a clarification, Liu Jun. Here is not a projector. Here just means all the U forms a complete basis, and there is a proper measure has been absorbed in the functional, like a D square bracket in that.
yeah, what is this measure?
this you can show that this is a hard measure. So yeah, if I consider if I have a like a set with case like sets, then let me consider discrete lattice. If I have case sets, then yeah, this particle this Hamiltonian can only like generate states that are like yeah, that is a irreducible representation of the SUK matrix. And then you can identify the proper high measure for it.
So in terms of phi, do you know the explicit form of this measure?
In terms of phi, I didn't work out this. I haven't thought it in that way. Yeah.
Thanks.
Yeah. But I want to say that if I consider additional like interaction terms, this is not a correct construction. So it only works when we have just like this bilinear term in the Hamiltonian.
Yeah, this is something I'm confused about. So
Yeah, maybe you
you mentioned multiple times that you have to use this quadratic Hamiltonian, but the statement that 1 is equal to this integral is a statement about states, which is independent of any Hamiltonian. Why do you have to refer to Hamiltonian?
yeah. What I know is that to be more general, like this like complete states in the Hilbert space should be like multiple like product of this exponential. And so this exponential kind of generate like a particle Hall excitation, and we can also have another like term that generate another particle Hall excitation. So if you like this is a like complete Hilbert space, and and that's the only complete Hilbert space for a Hamiltonian with particle Hall symmetry. But it turns out if I consider quadratic Hamiltonian, those other like states are not relevant. So like we cannot see those states, transitions between those states. So that's why we only consider this one.
I see. So in the equation 1 is equal to that integral, this 1 is the identity operator in the space formed by states that can be obtained by acting the Hamiltonian to some reference states?
Yeah, right.
Thanks.
Yeah. Yeah, okay, yeah. And yeah, then like with this construction, so this is the action we get, and it still contains the fermion operators in it. And what I want to do next is to get rid of these fermion operators. So by just making use of the like how fermion operators acting on states, we can it turns out we can get rid of the fermion operators and write down this action in terms in this form. So here this all these like functions with a tilde is a bilocal fields. So for example, this U tilde is defined as exponential of I phi tilde. And this phi tilde, the matrix element of phi tilde, relative to the position I and the position G is this phi ig here. And note that here all these products you should understand them as matrix multiplication. And for example, this distribution function f tilde here is generated by this u tilde in this form. And these are all matrix multiplications. And so far, I write down everything in terms of position coordinate ig. And next, I want to write them in terms of phase space coordinates. So now let's express this action in terms of phase space coordinates. So I mentioned it very briefly, like what do we mean by phase space coordinates? So let's consider because they are bilocal fields, so they have two positions that we use y minus and plus x minus and plus y over 2 to denote these two positions. And then what I do is to do a Fourier transform to the relative coordinate and keep the center of mass coordinate. And it gives me a new function in terms of center of mass coordinate x and the Fourier transform of relative coordinate p. And this is basically the Weil transformation. And in this phase space coordinate, the matrix multiplication of say two bilocal fields A tilde and B tilde can be written as a Moya product, which is in this form. And here this star is called the Moya product, and you can see that it can be very looks quite complicated, meaning that it contains infinite order of derivatives in this product. And so we can also work out what is a trace of the matrix product in terms of phase space coordinates. And it turns out it's very simple, and we can get rid of this Moya product and replace it with a normal product in this way. And with doing these tricks, so this is the action we get in terms of the phase space coordinate. And here, the first term, I forgot to mention. So this first term is a Wessel-Maynard-Witten term. It comes from the purely the time the time dynamics. And this second term comes from the Hamiltonian. And to make this analogy with quantum mechanics more one step further, we can also derive the equation of motion following from the action. So for quantum mechanics, this is a well-known equation of motion. And the same here, we can follow the same idea and obtain the equation of motion. And this is the equation of motion that we can obtain. And if you know about Keldysh formalism or then you probably recognize that this is the quantum Boltzmann equation. And if we take the semiclassical limit meaning that only keep the leading order derivative in this Moya product, we get the semiclassical Boltzmann equation, and this is the Poisson bracket.
Sorry, can I see the definition for U? Oh, yeah, it's here.
Yeah, the definition of U, yeah, is also written here. Yeah, this U is like exponential of I phi, but here all this this exponential should also be understood as doing the Moya product.
Why did you say the first term is a Weis-Wiener-Witten term?
Yeah, because it's that's a question I don't know how to understand, how to explain, how to say properly.
Usually when we say a Weis-Wiener-Witten term, we imagine extending the spacetime to one higher dimension and then demand the extension to demand the action to be independent of the extension, which imposes some quantization condition of the Weis-Wiener-Witten level. What's the analog?
Yeah, here right. I say what
Yeah, I have the same question. So this term looks like the term that when you do gauge transformation for non-abelian gauge theories, and also you do time evolution for for matrix Hamiltonian theories, then you will get this term. I think for Weis-Wiener term you will have 6 U's here, but you have only 2. So yeah, I'm wondering why this term is Weis-Wiener term.
so I honestly I don't know like I probably know much less than you guys about Weis-Wiener-Witten term. So my understanding is that if you get what like the extension Liu Jun said, can I say that basically if we like follow a time evolution, so we can capture like the a path like over the time, then we can get a phase term like from this action, and then we say that that's a Weis-Wiener-Witten term. So this is an analogy I learned from just the coherent like path integral for the spins for a spin.
I see. Is
And
is somehow the thing that imposes the commutation relation.
right, yeah. So for the spins, like the commutation relation, like basically like tells us that if we evolve in time, then we will pick up a phase like in this block sphere, right? So if we have a block sphere and if we evolve with time, we pick up this phase. And here, my understanding, so this is essentially the same thing as a spin. So you can also say similar structures. And so this one also like comes from the commutation relation of the bosonic fields.
So does the action depend on F0?
Yeah, it depends. So right, so this F0 is here, and yeah, it depends. If you expand it, probably you will see. Yeah. I will show you like one example when it like depend on very strongly on F0.
I see. Thanks.
Yeah. So at least you can say that it depends on F0. Yeah. From this let's now like expand this U like in terms of the phi field. And if we can also gauge fix this phi, and it turns out, so we can write this phi in terms of the position x and also and only the angular coordinate of the Fermi surface. And then we can expand and take the semi-classical limit, and this is the result we get. So you can say that this there is a PF here, the Fermi momentum, and that one can come from the distribution function.
So if the Fermi surface is not spherical or circular, how does it change?
That's a good question. That's also one question I want to understand. But so far I don't have a good answer. I think very likely we can still parameterize, we can still do the gauge fixing and get some angular coordinate. But now it will depend on also on get an angular right. We can I think we can also like parameterize it with just the theta, but there will be some measure like depend on the length, like the length, the Fermi local Fermi momentum. Yeah, but that's also one question I try to see, but now I don't have good answer to it.
Thanks.
Okay, so and this is an action that was found by DDMS when we expand to quadratic order in phi, and there are also higher order terms that are here. So the point I want to make is that this turns out to be very efficient when we want to compute the response function. For example, we can ask what is the response function, what is a density correlation function? And for density operator, the fluctuation of density, it turns out it can be obtained as a gradient of phi in position. And if you plug in this relation into this density correlation, you will find that it can be obtained by just the quadratic term in the action. So in contrast, if we want to calculate this quantity in terms of fermions, we need to do a loop integral. So this is one demonstration that this bosonized EFT may make some calculation of response functions more much easier. And however, so when we want to use this action to calculate orbital magnetic responses, it is more challenging. So the reason is because the magnetic field is not perturbative. And so it does more dramatic thing to the EFT. So next I want to discuss how to couple the EFT with a background magnetic field. So there are 2 points I want to make. So first, the dynamics should be governed by quantum Boltzmann equation, even if we are looking at a weak magnetic field. And the reason can be very intuitive, can be argued in this way. So we know that the semiclassical expansion is assuming that the gradient of x times the gradient of p is much smaller than 1. And let's see what happens when there is a weak magnetic field. So this gradient of x is at the inverse, is some inverse length scale. And you can intuitively say that it is roughly the inverse of the magnetic length, which is square root of b. And on the other hand, this gradient of p, it's some length scale, and it's roughly the cyclotron radius, and that is proportional to kf times lb squared. And if you put them together, you will find that in the weak field limit, this product actually is much greater than 1. So this tells us that even if we are looking at the so-called semi-classical limit for weak magnetic field, so we cannot just consider a semi-classical Boltzmann equation. We really need to use this quantum Boltzmann equation like I described in the earlier session. And the next question.
Sorry. Why should I identify the derivative of p with kf lb squared?
Yeah, my main intuitive understanding is that this p is relative coordinate. So it is related to the coordinate of 2 electrons. And we know that when we have these 2 electrons, the natural scale is the cyclotron radius. And yeah.
I see. Thanks.
Yeah, but it's just an argument. So we will make it more concrete. Yeah, in the calculations. Yeah. Okay. And another point is that when we want to gauge this effective action, it's we can do it by gauging the global U1 charge conservation symmetry. And after some change of variables, it turns out it's very simple to the action. So we just need to replace this Hamiltonian, which was like without magnetic field, just the epsilon p, into this epsilon as a function of p plus the gauge field A here. And A is a gauge, like in the symmetric gauge, like when there is a magnetic field. And so while this action looks very compact and simple, it turns out it's like you can think it's not very straightforward for you to solve, because so at each u there are like exponential in the I5, the phi field, and we basically have a very nonlinear action with infinite number of irrelevant terms. So with just this, it's not clear for us how to proceed, especially given that we cannot just replace this Moya product with Poisson bracket, with we cannot expand this Moya product. So like let me give you some hint on how to proceed, and then let's first say so what are the real problems here. So as I mentioned, so this is a non-perturbative problem in nature, even in arbitrarily weak magnetic field. So you can understand it by this argument. So this Landau wave function, we know that we can solve it, and it cannot be perturbatively connected to a plane wave basis. So in terms of symmetry, that means this crystalline translation symmetry or continuous translation symmetry for the parabolic band is reduced to a magnetic translation symmetry. And also, this problem is non-commutative in the following sense. So if you think about this momentum k, the mechanical momentum, so I should say it's a mechanical momentum, it's no longer valid at first sight. So it's no longer commuting variables. So let's define this mechanical momentum k as p plus ea, and there is also another variable called r, which is the coordinate of the guiding center in the symmetric gauge, and it can be written in this way. And we treat them as quantum operators, so we find the following commutation relation. So in this sense, they are no longer just commuting variables. And in other words, the fields we are talking about in a magnetic field, they are living in a non-commutative manifold, even in a arbitrarily weak magnetic field, because this the dispersion is written in terms of k. So I also want to say that these two challenges are also connected with each other, because this variable r, it can generate the magnetic translation, and also this k variable, the kinetic energy only depend on the k variable. So Liu Jun, I want to ask how much time do I have left?
I don't want to impose any time constraint, so you can take as much time as you want.
Oh, okay. I guess I shouldn't take too long. Okay, yeah. Let me try. Yeah, but please feel free to ask questions. So, right. So, with this, inspirations. So we realize that to simplify this problem, we can actually define a coordinate transformation, from the phase space coordinate to this RK coordinate. And then this gauge the action, like written in this RK coordinate, becomes the following. So like you can see that the dispersion of the only depend on the K coordinate. And for this reason, the ground state distribution also only depend on K. But the fluctuations are written in terms of U depend on both K and R. And this Moya product can also be written in terms of RK coordinate in this way. And you can see that we can separate the two and we can write them as tensor products of the R part and the K part. And it is also related to the fact that the commutator between R and K vanishes.
Oh, sorry. Just to make sure. Here, this P, on this slide, the P is not gauge invariant, is it?
No, it's not a gauge invariant.
So just by looking at this action, how do I know that this action is gauge invariant?
Oh, okay. So if you gauge this action, yeah, it will like this, yeah, if you, basically, I guess you want to ask like whether this one is gauge invariant, right?
And also the first term.
Yeah, this F depends on U. So basically whether this U is gauge invariant.
Mm-hmm.
So what one can do is that we can yeah, we basically the gauge yeah, let me see. The gauge yeah, under like this U1 gauge transformation. So what we do is that we the final result is that we will like replace P with P minus partial like gradient of lambda, and the gauge transformation is defined as e to the power I lambda, the U1 gauge transformation, and then right, so yeah, at the beginning, so we let me think. I'm a little bit forget what. Right. Okay. So this F can be written also as a sorry. Yeah, I think you are right. So this one, I should write it as X and K. Yeah, so because I did some like coordinate transformation and make it a little bit like weird now. So what I should really write is, yeah, okay. Let me go back to this slide. So what is really done in this gauging is the following. So so I can ask what kind of action can leave it invariant under global U1 transformation. And then the action should be X P minus A. I think there is a minus sign. And then you can check that under the gauge transformation, this P will change to like P plus or P minus gradient of lambda. And this A also change accordingly. And as a result, this term is invariant under the U1 gauge transformation. And then what I do next is to do a coordinate transformation and basically define it as a P prime here. And then this one becomes P prime plus A. And I call it this P plus A here.
Mm-hmm.
So this is right. So if you want to gauge it, what you should act on is not this action. It's not this dispersion, but this field F here. And so the reason is because you can first define a global. You first, because you can show that if you define a global, you can first define a global U1 charge conservation, and then you gauge it by making this lambda spatially dependent, and then you realize this is a correct way to define the gauge transformation.
Do you
So
need to
this-
do this then? Do you need to do the same thing to the first term?
For the first term, right, for the first term here, I should replace it with K, with P plus A.
So I'm confused about one thing. Initially, when you started from the coherent state path integral, and you focus on states with a fixed particle number, then for these states, the U1 transformation, if I really fix the particle number, then the U1 transformation can be defined to be trivial, right? I can, by fix the particle number, I can choose my convention to say that the particle number, the charge, the U1 charge in this particular sector of particle number is equal to 0. So the U1 charge conservation symmetry has no action. If you really fix the particle number, then if from this point of view, when you do gauging, is this what one should do? Maybe a more basic question. Before gauging, what is the electron operator in this theory?
So the electron operator is
Here in this action, the fundamental field is that phi. So in terms of phi, what is the electron operator? Is it just e to the I phi?
not exactly. So it is EP CP. And then it's a density operator. It's basically the trace of the density operator, and then you can find that it is this one times F P, like integrating over P.
I'm asking about the electron creation operator.
Oh, electron creation operator. Yeah. So here there are two separate questions. So for electron creation operator, it's not written in this action. So it's not e to the I phi. So e to the I phi it's not e to the I phi. E to the I phi gives you the particle hole excitations. So the one thing is that this action doesn't have the electron, single electron creation operator or annihilation operator.
Because you fixed the particle number.
I think we cannot say that because it's fixed the particle number. So if it fixed, we don't include the process that have particle hole excitations so far.
But in principle, in the full quantum theory, I do have electron creation operator. If I have
Right.
if the theory is about to capture the physics, I should be able to know what is the electron creation operator, right?
Right. Yeah, that's also one thing that I don't like, or I think one should understand better about the Coadjoint-orbit approach. So far, I think this action doesn't really have the electron creation operators. But I want to like warn you one thing you may feel concerned later. So while I construct the action like for fix the particle number, so we didn't do it accurately, but we say that we can consider a grand canonical example, namely that we can add the chemical potential and fix the chemical potential. And so we didn't include the physical process that changed the particle numbers, but we count all states with different particle numbers. So we have included that part into the action, so not implicitly here. Yeah.
If you do that, then in principle, you should have the electron operator, creation operator.
Right. So if I just say I count the states in different particle number sectors, I don't have the electron operators. But indeed, I think to completely understand the theory, so we should know how to write down the single particle like operator.
I'm actually not sure I agree, because the Boltzmann equation doesn't have that operator, right? The Boltzmann equation always has a creation and an annihilation operator. So I think if the goal is just to describe the fxpt, then maybe you don't need to.
If you only describe the f for, then maybe you don't need it. But there are other physical quantities which is not described by f, like the alpha spectrum.
I see. Well, then
in fact, that's exactly Duncan. Sorry for the interruption. I mean, exactly the electron operator is what Duncan like constructed in his paper for one-dimensional system. But in the most bosonization formalism, because of the conservation, like all the excitations are described in terms of the particle hole pair excitation sectors. So presumably, like the Klein factor will drop out at last. So.
In 1D, the electron operator is described by Duncan's work. I'm not sure whether it's
Yeah. I mean, here it's a non-trivial construction. Perhaps we can rescue whatever defects here, but I guess you will see it will factor out, and like the most important excitations comes from the like density type excitations.
Some physical quantities, like the alpha spectrum, they are just not density correlation function. One has to understand the electron creation operator in order to understand the alpha spectrum.
So I'm not sure. Yeah, or like if I want to ask like how to generalize it to non-Fermi liquids. So in that case, like in the conventional approach, so we can calculate the Green's function, and even for that case, it's not clear to me like how to proceed without like knowing about the single particle, like how the single particle operator acts. But I heard like maybe Uma, they have some answer to this question already.
I see. Thanks.
Okay, so okay, yeah, so this is like the simplified action we have. So why I say it's a simplified is because it turns out that we can make use of like we can separately study what happens to the r coordinate and the k coordinate. So first thing you can say is that this r coordinate, it doesn't like determine any dynamics like any like this kinetic energy. So as a result, so this system has a symmetry. So it's in other words, the system has a symmetry, which is a magnetic translation symmetry. And it turns out we can make use of this fact to integrate over R, while it appears it looks quite complicated in this this Moya product. And the result, I'm not going to discuss it in detail, and just want to say that the result is that it will give us the Landau level degeneracy. So the basic idea is that, so at the operator level, so the R doesn't appear in the like Hamiltonian, means that they commute with each other. And like in terms of coordinates in this field theory, so we can show that there are no couplings between any physical observables, including the distribution function labeled by different eigenvalues of the magnetic translation generator. And then we can make use some like very simple techniques in non-commutative field theory, and also use properties of this magnetic translation to rewrite this action only in terms of the k coordinate, the physical momentum. And this Moya product now is also only in terms of the like this k coordinate. And but we have n phi copies of this identical theory, and this n phi comes from summing like integrating over R, and n phi is the Landau level degeneracy as I defined here. And then our next task is to like try to simplify this theory only in terms of the k coordinate.
I have a question concerning dropping out of the R. And so, like in terms of the fractional quantum Hall system, I would like to understand R as guiding center operators. And in the presence of the interactions, I do have non-trivial like terms, including those R's. So you said your formula is supposed to be applicable to like interacting systems as well. So I don't see like in the presence of the interaction why R will also be dropped out in general.
Yeah. Like we hope that I will hope that this formalism can be applied to like the interacting case. But in that case, I think we cannot just drop out the R. We need to study the structure due to the R. Yeah, but so far we haven't gained much progress. Yeah, we are trying. This is kind of one question for us. Yeah, we're trying to understand.
Okay, thank you.
And then like let me like show you how we can understand this simplified like action. So here we can use make some semiclassical expansion in the k coordinate. So here let me like just write down the term in the exponential, and then we can estimate that it will depend on b over the square of the like Fermi momentum, and you can like find that it is proportional to omega c over mu, which is much smaller than 1. So as a result, in this Moya product, we can expand it for k. We can expand it to the leading order in B to get the like the leading order effect from B. And so next, let me show you the action expanded in terms of phi here, and also in B. And this is the action we obtained. So this comes from the time-dependent part, and this comes from the Hamiltonian part. And here, the bracket are the Poisson bracket because of this expansion, and it is defined in this way. And I also want to say that emphasize that these bosons are compact bosons because they appear in this U in this way. And so and in other words, these bosons can have winding configurations in time and in momentum space. And first, let me forget about the possible winding configurations, and also fix a gauge for the field phi such that it only depends on the angle theta, where theta is the angle on the Fermi's of the Fermi momentum in the Fermi surface. And we know we consider like a parabolic band, so the ground state distribution only depend on the radial coordinate of K. And now let me walk through you through what action we should get. So because we don't consider winding configuration, these two terms turn out to be total derivative terms, and then we can drop them. And for this the second term, like quadratic in phi, so we can like flip the Poisson bracket and get this term, and it turns out to give us some non-zero contribution. And for the cubic in phi term, so we can also like flip one of the Poisson bracket and get this form. However, because the second Poisson bracket depends all on the angle theta, so this term vanishes, and we will get 0 for this one. And for the Hamiltonian term, following the same argument, we will find that the cubic term and the higher order terms vanishes exactly for quadratic dispersion. But if we consider cubic dispersion, we will get additional terms from the like nonlinear terms in phi from the dispersion. And now let me like just write down what we get for the quadratic dispersion. And this is a chiral boson action. So you can see that you can see that we have n5 copies of the chiral bosons. And now let me give you some physical intuitions of this action. So on the one hand, we can see that we can take a semiclassical picture. And so this is essentially an action in the semiclassical limit. So it describes a field that is moving on the Fermi surface, and with a velocity omega c. And on the other hand, we can solve the spectrum of this action, and we find that you can say it that the spectrum should be integer multiples of omega c, and it has a correspondence with this Landau level picture. So in the Landau levels, we feel like if we ask what are the particle hole excitations of the Landau levels, so we can say excite this electron to the empty Landau levels, or excite this electron to the empty Landau levels. And this particle hole excitations energy is integer multiples of omega c. And this is exactly described by this chiral boson action. And however, so we know that to completely understand this bosonized action, we need to reproduce all the response functions, including the quantum oscillation, which will depend on the Fermi surface area. So the question is, where is the Fermi surface area or the chemical potential in the action? So it's not here. And what's missed is the contribution from the winding configurations. And let me go through give you some ideas or pictures of the contributions from these configurations. So first, we can ask what's the physical meaning of winding configurations. So we can, for this action, we can define the density operator, at the angle theta as a partial derivative of the phi in theta. And then we can do a mode expansion of this compact boson, and we get this bunch of terms. So the summation term, if you integrate over the angle, it's 0. So it tells us it preserves the particle number. So they denote the particle hole excitations. However, so there is also these terms that doesn't vanish if we integrate over the angle theta, and they physically correspond to adding or depleting the charges from the ground state configuration. And now let's include, and these are also the zero modes because they doesn't they have angular momentum 0. And now let's ask what are the contributions to the action from these winding configurations of 0 modes. So it turns out that this action, the winding configuration contribute to the following term in the action. So I'm not going to explain the second term, but for the first term, you have seen it from the previous action. So it's a product, it's a total derivative term, and it's a product of the distribution from ground state distribution function and the time derivative of phi. And so then this term, when you integrate over the Fermi surface, it will give you the Fermi surface area. And now we can plug in this 0 mode winding configuration into the action, and this is the action we obtained in terms of Q and P here. And the first term comes from the total derivative term, and so this its coefficient is mu over omega c, and you can also say it as depending on the Fermi surface area over another momentum scale. And so this one is just the action for a particle moving on a ring, and we can integrate over the coordinate q, and that will give us a constraint that p has to be an integer, and this is a partition function we get from integrating from this 0 mode action. And here this delta as a function of mu over omega c basically is a fractional part of mu over omega c. And as you can see here, so this action should be, this partition function should be oscillatory in this quantity. So in other words, it's oscillatory in 1 over b.
Sorry, can I ask a question? So
yeah, sure.
Mu is chemical potential?
Yeah, mu is a chemical potential, right?
So mu over omega c is dimensionless.
Right, yes.
And p here is also dimensionless?
Yeah, p is also dimensionless.
Then how do
Yeah,
the first
it's an
two terms
integer.
have how do the first two terms have the same dimension?
How
Did you
do
mean
the
q dot? The first term has dimension of q dot, the second term has a
you are right. Yeah, right. You are right. So I miss a q dot. So this part will give me the constraint that it's an integer. Yeah. Right. Sorry. Yeah.
But I think
yeah, this is
way,
yeah, please.
Maybe a simpler way to see that p is an integer is just to look at its definition, right? Phi is equal to q plus p theta and so on. Theta is angular variable. So theta
actually,
theta and theta plus 2 pi should be identified. So p should be an integer.
Oh, you mean looking from here, right?
Yeah, so e to the I phi and e to the I phi plus 2 pi is the same thing, and theta plus 2 pi also the same thing. This already requires p to be an integer.
So it's not exactly like this. So if we integrate out this q, so the constraint we get is p minus mu over omega c equals to is an integer. Like that, let me use this p tilde to denote an integer. And then what actually this p here should be this p tilde.
So what did I miss when I said the previous argument? What did I miss in the previous argument?
So your previous argument is that because it's e to the I phi.
Yeah, you said phi is an angular variable, and here theta is also an angular variable. Because theta is an angular variable, so theta and theta plus 2 pi should be identified if we only consider e to the I phi. Doesn't this already require p to be an integer?
So it seems so, but yeah, I understand your argument. Yeah, let me think what's the problem here. Yeah, sorry, I don't have a good answer. Let me think about it and get back to you.
Sure, thanks.
Yeah. Okay. Yeah. Let me let me like also give you some like physical intuitions of what this like partition function of the zero modes means. So here, so this is a Landau level picture we showed, and we can put a chemical potential and ask, given we have this chemical potential, what is the energy cost when we add or deplete electrons, like relative to the ground state configuration, the ground state. And this energy cost is essentially described by this part of the partition function. And we can say that so it like it depends on where we put the chemical potential because because as we vary the chemical potential, the energy cost would be different. And this explains this dependence in omega over mu over omega c. And so from this, like adding both the winding contribution from the winding configuration and the and also the oscillatory contribution, so we can reproduce the exact LK formula, and also that naturally give us the oscillation, magnetization, diamagnetic response, and the specific heat, etc. And so the last, let me give you some outlook of like what we think, what is our like our idea to generalize this EFT machinery for a generic band in a magnetic field. So the procedure we hope to achieve is that given the band, like a bunch of bands, we can ask how the interaction and also the magnetic field project to a given band near the chemical potential or given bands near the chemical potential of our interest. And this band does not necessarily have to be parabolic, and so it can have some, like the Fermi surface can have some non-trivial shape. And so this requires us to understand how to incorporate the interaction effect of the block wave function and also the shape of the Fermi surface into the theory. So we are still working on it, and here I want to give you some picture of how we think about the effect of the block wave function, like using a approach of band projection. So we can try to we can start from a matrix Hamiltonian, after the gauge, the coupling to the gauge field. This is a Hamiltonian in the matrix, and then what we can do is to start diagonalize this Hamiltonian into the diagonal form, and then we can ask how this energy of dispersion of the band A depend on the dispersion when we don't couple it to a magnetic field. I define as epsilon of 0 here. And it turns out that to the leading order in B, so this effect can be obtained, captured by a change of coordinate from K to K minus this quantity. And here this A depend on the is obtained from the block wave function. Is essentially the connection in the momentum space. And also there are higher order terms we can calculate systematically from this band star diagonalization. And with this new coordinate, we can show that the winding it has a the winding configuration is corrected by a term that depend on the total Barry phase enclosed by the Fermi surface. And I think this result has been obtained earlier using the semiclassical approach. And we can also capture it here. And we can also in principle ask how the Barry connection, we can also obtain in principle know how the Barry connect curvature affect the Hamiltonian part of the action, and that will give us not only the correction of the Barry phase to the oscillation frequency, oscillation phase, but also the oscillation amplitude. And this is a work Yuxuan and I are doing recently. And also, so I want to point out a duality of this weak field Fermi surface theory with a strong field with a quantum Hall edge theory in the strong field limit. So some of you who know about the quantum Hall effect probably have found that. So it's very similar to the chiral boson in the in the real space describing the edge state of a quantum Hall droplet. And so this can be made quite precise by building a connection between the Moya product of in terms of K for the weak field limit, and also the Moya product in terms of X projected X coordinate in the strong field limit. And this is a work I'm doing with my postdoc Wang Jie. And so let me summarize. So this is the picture we had for the effective EFT in a magnetic field. So let me highlight that. So from it we can match exactly the partition function solved using the Landau levels for the free electron gas. And we also demonstrated the topological origin of the quantum oscillation. And lastly, so I want to highlight that we can construct this bosonized EFT without solving the fermion spectrum in a magnetic field. So this gives us a hope that we can generalize it to more interesting cases. And with that, yeah, thank you for your attention and questions.
Thank you for the very nice talk. Any other questions? Let me ask a quick question. So,
yeah, sure.
You discussed this chiral boson in the context of parabolic bands. Should I expect the chiral boson for any band structure?
So what I understand is that for let's say still for circular Fermi surface, but for cubic band, so it's not there will be cubic terms in the action. So it will be still have this term, but In addition, there will be interacting terms.
Are they irrelevant?
So I think they are irrelevant. Yeah.
Well, what about Dirac dispersion?
For Dirac dispersion, I haven't looked at it. I thought it's irrelevant as well. But there is something I didn't think very carefully about. But one thing is that we need to put the chemical potential well above the Dirac point.
Yeah.
Yeah. So it seems to me it can only see the deviation from this equal Landau level spacing perturbatively. So essentially the reason it's it's a chiral, like if it's a free chiral boson, that means the Landau level spacing are like the same. And if it's other dispersions, the Landau level spacing are different, and that effectively will give us the high order terms.
And also with Dirac fermion, there's also the Berry phase.
Yeah, there's a Berry phase. I didn't check the Dirac fermion, but I think it should be able to be captured by the Berry phase. I showed, like using the band projection.
Okay, thanks. Any other questions?
One quick one. If you have multiple bands, does this approach capture interband coherence and tunneling and things, or?
So by multi-bands, you mean that there are also multi-bands near the Fermi surface?
I wonder, is that within the scope of this approach, or because you're choosing a slow temperature, you never have to worry about?
I think we need to worry about it, but then when we do the band projection, we need to project to multiple bands, and then this very connection is also the non-abelian ones.
Yeah.
So we need to do some modifications to it. I think it seems to me it's hopeful that it like for this it can be done.
Okay, thank you.
Yeah.
Any other questions? Yeah, if not, let's thank Mengxin for the next talk again. Thank you.
Yeah, thank you everyone. Yeah, Liu Jun, I will get back to you the question you had. Yeah, thanks for asking many very nice questions.
Yeah, thank you. And now I will stop recording, and we can leave.
Recording stopped.
Yeah, bye.
Yeah, see you.